Good morning, AP Physics. We're going to miss each other again, and because of that, again, I feel the need to send you some more information. Not real hard ideas, but you need to have seen them, and probably coming from me would be a little more familiar, so I'll do that. Back in regular physics, we talked about elastic collisions and inelastic collisions, and to be honest with you, we did not give you the correct definition at that point. We didn't feel that it would be that big a deal for you. So I need you to know the truth now. When things collide, we have elastic collisions in which kinetic energy is conserved. Now remember, energy is always conserved, but when you have two objects that hit each other, some of that initial kinetic energy can easily go into sound energy, heat energy, things like that. So if we're talking about what's called an elastic collision, none of the kinetic energy that was there presently, to start with, gets converted into any other kind of energy when the objects hit. The total kinetic energy of the system is the same in the beginning as it was at the end. Weirdly enough, if it's inelastic, well then kinetic energy is not conserved. Energy is always conserved, but in an inelastic collision, kinetic energy is not conserved, and thus some of the energy is transformed into heat. Sound, I suppose light, if there were some sparks, things like that. For whatever reason, they called a perfectly inelastic collision. That's when the objects stick to each other. And that could happen if two football players stick to each other. If two cars hit and for some reason they travel together, you can easily have a perfectly inelastic collision. And in that kind of a collision, lots of the kinetic energy is transformed into heat, sound, other forms. In real life, this probably never happens. You're generally going to have some of the energy transformed into some other form. But it is a theoretical thing that we need to talk about. And I do need to just get the definitions down. Elastic, kinetic energy is conserved. Inelastic, kinetic energy is not conserved. Total energy is always conserved. But that's the kind of things we're looking at. Let's take a little look at what happens to the math a little bit when you do look at an inelastic collision. So this is just the example right off of your notes. So if you want to pull those out at some point, look at them, feel free to do so. There's two billiard balls heading at each other. Here's the mass and the velocity of the first one. Here's the mass and the velocity of the second one, and they are heading at each other. My vectors are not probably quite the right lengths. So remember too, momentum is always conserved as long as the forces involved are only internal to the system. So let's say these two things are going to hit each other. There's no friction, there's no air resistance, there's no things like that. The beginning momentum, well, we could calculate that. Momentum is just mass times velocity, so I did that, mass times velocity, plus the mass of the other one times velocity, and I call this negative because it's heading in the other direction, and I just add those up for you, that's what you get. The final momentum has to be the same. So mass times the velocity after the collision, I don't know that. And I took mass times the other velocity as well. I don't know that one either, that's why we have two different velocities, V1 and V2. But since momentum is conserved, the total momentum has to be the same as it was before. This is an elastic collision, so the kinetic energy is also conserved. Again, whether that's really true in real life, don't worry about that for now. But here's what I did. I found the original kinetic energy. 1/2 times mass times velocity squared, plus 1/2 times mass times velocity squared. I didn't bother to put in a negative 20, because we all know that when you square it, it won't matter whether you started with a negative or positive anyway. And I added those up, and I left everything in grams here. You could change into kilograms, you can leave it in grams, as long as you're consistent throughout, it actually doesn't make any difference. I do have to be careful. This would not be joules. I guess we would be in millijoules, since I'm off by a factor of 1,000. Anyway, this is the original kinetic energy. Well, the final kinetic energy must be the same, because this is an elastic collision. So once again, 1/2 times m times the unknown velocity squared, plus same thing here, and the total has to be the same. Here's what is the difficult part, and I'll be honest with you, there's one of these on the quiz, you get 80 or 90% of the points simply for setting it up. If you can finish and do the math, great for you. If you can't, don't worry about it. We need to solve a system of equations. Here's one of them, and we've seen this before. There are infinitely many solutions to that. Pick a V1 and there's lots of V2, or there's a V2 that'll work. Nobody can solve that because there's two variables. Here's a second equation that nobody can solve either because there's two variables in it. However, if you look at these two, this is a system of equations. I don't know how you want to solve it. Geometry-wise, this is a line and this is an ellipse. So we're actually asking, where does this shape, an ellipse, where does it hit a line? And I think I'll probably just do the math separately and send it to you. I'm not that worried about the math. I'm worried about the fact that you know what the words mean, and can you set up a system of equations for an inelastic collision. That's the biggest thing that you need to be able to do. Again, there's only one of those on the quiz. I'm not that worried about the math. The other thing that we haven't had a chance to talk about yet is something called a ballistic pendulum, and this is a ballistic pendulum. The general use of this is they'll take a real gun, this is not a real gun, and shoot it into a block of wood that then swings up. And the point is to use some math and some physics to go backwards and figure out the velocity with which the gun shot the bullet in the first place. That's what the use is for. That's why it's called ballistic. That has to do with bullets. So anyway, we shoot something into this. This would then swing up. And the whole point is that we can use conservation of energy and conservation of momentum. Remembering, however, that conservation of momentum only holds when there's no outside forces. So here's a picture of how this thing works. Again, it's called a ballistic pendulum. We generally shoot a bullet into a block of wood. The whole thing swings up. You could use two ideas. From right before the bullet sticks to right after it's stuck in a block of wood, during that very brief period of time, no outside forces, you get to use conservation of momentum. So the momentum of the bullet all by itself, right before the collision, equals the momentum of the block and the bullet stuck in it right after the collision. After that, as this thing swings up, you can't claim conservation of momentum because there is an outside force called gravity. You can, however, use conservation of energy, and we're free to do that. So the kinetic energy of the block of wood with the bullet stuck in it equals the potential energy of the two of them when it swings up to the top. So actually, even though the motion goes forward, we use the ideas in reverse. So we do get to say this, that the kinetic energy of the block with the bullet stuck in it at the bottom is equal to the gravitational potential energy of the two of them when they swing up to the top. And I've asked you guys to give me this kind of communication before. Some of you are doing a good job of it, and some of you are still struggling with that. That's the kind of communication that I need to see. Based on the masses here, this was in kilograms, this was in grams. The kinetic energy at the bottom is 1/2 times the total mass of the two together, times the velocity squared, which I don't know yet, equals the gravitational potential energy of the two by the time you get to the top. Again, total mass, acceleration of gravity, I changed 6 centimeters into meters, and you can go through and solve that equation. You guys can all do that math. When you do so, here's what you get. Back up, we're going to use that idea now. Once again, right before the collision to right after this collision, momentum is conserved. So all I did was take the momentum of the two together, here's the mass of the two together, there's the velocity of the two together, back up a split second before that, that momentum has to equal the momentum of the bullet all by itself, and there's the mass of the bullet times the velocity of the bullet, and you guys can all do the math to solve that, and I'd like you to do so. We are still planning on having our test on Monday, and what that means is when you come in tomorrow, Friday, you need to have just about all your homework done, and you can either have a chance to ask questions on that and or work on the lab if you need to do that. Hope to see you then. Good luck.